Swayam Prabha. Digital India. Educated India.
Good afternoon and welcome to the lecture 32 of this NPTEL online certification courses on environmental degradation of materials and surface engineering. We are into the second part, which is basically surface engineering part, and in the first part you have already learned about the various forms of degradation of materials. So this is lecture 32, which is the second lecture in module 7. And if I straight away take you to the statement that I made in the last lecture, at the end of the last lecture, I did mention that surface engineering essentially is an exercise where we try to tailor the surface structure or microstructure and or composition. That means I can do only tailoring the surface microstructure and structure and leave the composition unchanged, or I can do both. I can change the composition as well as the microstructure. And as a result, the objective is to improve the surface properties from the pristine form. So that means I can protect the surfaces and the bulk better than what was possible before. So that suffices, that conveys the major objective. So surface engineering is a generic approach towards enhancement of the performance of engineering components or solids with respect to various forms of degradation, possible degradations. Like it should give you resistance to corrosion, to wear, abrasion, oxidation, sulfidation, or various other forms of chemical attack. It should enhance mechanical properties, not just mechanical, but even functional properties like electrical, electronic properties, thermal conductivity, emissivity, catalysis, insulation. It should also help you reduce friction coefficient when you want them. When you don't want, you can even make it rougher and increase the friction coefficient. So that means basically I can change the tribological properties depending on my objective. So either it can make the surface smoother or rougher. But of course I am also interested at times, and why at times, and most of the times, I mean, starting from applying a layer of cosmetic powder on the faces to providing certain glittering coatings on metallic objects, including the ornaments. In all such cases, aesthetics are very, very important. Now, this is quite a bit of a complex and a busy slide, but nevertheless it actually allows you to capture the entire scope of surface engineering. So again, let's remind ourselves, we are interested in tailoring the surface microstructure and or composition so that surface dependent properties of various types can improve. And in the last lecture, I did make a mention that we are interested primarily in three categories of surface dependent properties, namely the physical, mechanical or chemical properties, or in other words, which are dependent on these kind of activations. And as you can see here that there are three major approaches of surface engineering. One is, and this is very simple to follow because this is all dependent on the physical dimension. So imagine you have a bulk and you are interested in improving the surface protection or the life of the component. So you can do that by three possibilities. One is when you don't change the dimension, but you do something to the bulk, or more precisely to the surface in terms of changing microstructure or composition, so that you actually improve the life of the component. And in order to do that, you can apply thermal activation, mechanical activation, or chemical activation, and so on and so forth. Another very often practiced and known approach is removal of material. So whenever you are polishing material to make it shine better or appear more glittering. Or if there's a rough surface, you would have seen the in the wooden furniture shop, the carpenter actually uses a chisel to make the surface smoother and smoother. Similarly, you would have seen one who is dealing with either metals or stone objects, and the artist or the artisan uses a chisel to hammer and chip off stone chips so that the surface is smoother. So those are very crude and very large scale examples. But on the other hand, you also require not only solids or wooden objects, even clothes and various other forms of apparels which are of use to make it appear more shining and more decorated. These we can do again using a mechanical means or electrochemical or chemical means. Finally, there is this is more widely applied and more widely understood mechanism of surface engineering, which is by addition or coating a new material, either the same or the new material, and in the process you can take care of improving the chemical, physical or electrochemical. I mean, you can do that by chemical, physical or electrochemical means, but you certainly can improve the life, improve the functionality and various other things. So depending on what kind of an approach we are taking, as I said, so let's keep in mind that we are talking about three possibilities. Either we don't do anything at all to the dimension, we keep the dimension fixed, and yet we do certain modification in terms of composition or microstructure. Actually, whenever I say that we are doing something to the composition, technically speaking or more precisely, without changing the dimension even by atomic thickness is not possible. But what we are, when I say dimensions unchanged, I mean not to be seen or felt very easily. So you don't see that whenever you are giving a very thin coating or a very thin film, you are changing the composition though, but you are not quite able to understand that the thickness has changed. Similar things that when you subject to some mechanical or thermal activation processes, you do change the microstructure, but the dimension, I mean the overall dimension, the macro dimension doesn't change much. And under that category, if I just give you now specific examples, you realize that why, what are the kind of techniques we are talking about. The first one basically, and I've decided to use different colors so that you know exactly that the process of activations are different. Here, all are thermally activated processes. What am I doing? Let's say I'm dealing with a semiconductor device and I have implanted ions on the surface, and that makes the band, that changes the band gap of a particular region, and it actually allows actually the conductivity level to change. So I do a stress relief by in a process which is thermally activated called annealing. I can do that annealing isothermally, or I can do by rapid thermal annealing, which is basically through a flash of light or a flash of a particular temperature profile. So it's not isothermal, it basically is a profile like this. Then I can do surface hardening, where I can subject the steel components in particular to a sudden heating, either by oxyacetylene torch or a flame, or by induction, electromagnetic induction to the surface, confined to the surface. I can even irradiate with a laser beam and do very specific locations, do treatment or subject to treatment to very specific locations where I actually am able to subject that small volume to a thermal cycle, and it goes to room temperature to high temperature, stays for a while and then comes back. And in the process of heating and cooling, I change the microstructure and bring in certain wear resistant properties. So this is all by thermal heating. I can do by shot peening, for example. When I say shot peening, then I mean basically imagine small spherical objects. In the limit, you can even think of sand particles if they are spherical altogether. Otherwise, you have to take metal shots, maybe steel balls or ceramic shots, and you throw a large number of them, a large population of them, you throw at some specific speed, or so they carry certain momentum, they hit the surface and create a very thin deformation region on the surface. And that's actually helpful because by way of deformation, they also introduce residual compressive stress and improve the fatigue and some other mechanical properties of the particular component. I can do a similar thing by ultrasound peening or laser peening. Similarly, one can do by a very thin deformation layer by cold rolling, skin pass rolling, even by hammering. In all these cases, as you can make out, be it shot peening or laser peening or ultrasound peening, even hammering, you introduce certain deformed layer on the surface confined to very thin, ultra thin layer on the surface, near surface region, about a few, certainly less than a micrometer. So in such cases, you actually are able to introduce not only crystalline defects, increase their density, but also in the process create certain state of stress which are helpful. I can do by thermally activated process, what is known as diffusion coating on non-ferrous metals or ferrous metals, or I can do by, even I can bring in certain functionalities, say control grain orientation or microbial growth, or bring in certain specific texture on the surface. These are all possible by thermally activated processes. I can also think of some very special categories where I am modifying the composition and the state of stress both by ion beam implantation or mixing, or even plasma ion implantation. And obviously, chemical method is another possibility where I can change the surface composition in a very controlled manner. Now the second category, the removal process. We all know that whenever something has picked up some dirt or appears to be a little bit tarnished, the immediate tendency for us would be to rub it against a surface and make it appear shiner. In fact, the common experience of all of us would be that when we go to buy a brassware, go to a curio shop or of a person selling such art objects, moment the shop owner picks up a metallic vase, maybe a brassware from the rack, instinctively he would start rubbing it with a cloth soaked with some chemicals. Why does he do that? Why does one do that? One does it primarily to make sure that whatever layer of tarnishing has happened over a period of time can be removed by way of such polishing operation. So these are removal based processes. Now this is a very commonplace example I took, but you certainly can polish by way of mechanically grinding or polishing, or even chipping off some layers from the stone objects or metal objects. You can do that by mechanical activation, and which could be a manually operated process or a machine operated process. For example, if you are grinding a huge 1 meter diameter roll weighing a few tons, several tons, you can't do it manually. So you have to have a device which will rotate the roll at some RPM, and you'll have a grinding wheel and you bring on top of that machine, on top of that roll, so that the grinding wheel rotating at a very high speed and having much higher hardness and surface characteristics is able to remove the rust or surface marks or undesirable regions and make it flat and smooth. We can do a much more precise job in terms of electrochemical processes like electroplating or electropolishing. In fact, we can use multiple deposition layers and so on. We can also do by chemical processes where we actually allow a certain chemical reaction to take place or certain removal to happen because of the action of the chemical. And these are the typical operations in the removal based processes: rubbing, polishing, buffing, scuffing, chiseling. So obviously this is for stones, whereas this can be for metals and even for ceramics. grinding and polishing are relatively coarse processes where the rate of removal, depth of removal are very high, but the machining and turning actually are more precise, but again the depth of cut could be higher. On the other hand, if you are going for more precision surface engineering by removal, then you'll go for electrochemical polishing or electrodischarge machining, plasma cleaning or etching, and even focused ion beam etching or material removal. And there the precision could be to the level of a few nanometers. You can also do deep greasing or deep cleaning or greasing or chemical polishing, even etching to reveal certain objects or features on the surface. The third category, of course, is more routinely applied in various places, not just for heavy-duty engineering shops, but even in shops which are interested in selling art objects. So there again the three possibilities could be chemical in nature, physical in nature, and electrochemical in nature. And they can be treated using liquid or molten bath. They can be done through solid state processes, even through solid vapor interaction processes. And so similarly, the physical process can be done by vapor-based deposition or spray coatings or sputtering, even ion plating. And electrochemical process, we all know essentially is the so-called electroplating or electrolytic deposition process, where the cations move towards the cathode and get deposited on the object that you want to create a coating on. So these are the techniques that we routinely use in various forms of addition-based surface engineering methods. Galvanizing, I mean, if you go to a steel plant, or if you are going to use steel sheets in particular, or wires, even various forms of steels in thin sections, invariably you'll see that they have a thin layer of coating of zinc, and usually these are done through hot dip method. So you have a tank, you have molten zinc, actually it's zinc aluminum alloy, or maybe with some other variants of composition, and through which you actually allow the sheet or the rod or the wire to pass through with a certain statistically average residence time, during which the molten metal starts dissolving a part of the solid that is passing through, and by the time and in the process the zinc also is able to wet the surface well or adhere to the surface well, and as soon as the material, the solid, either rod or sheet or wire, is withdrawn from the bath, it undergoes a cooling cycle within which a zinc-rich layer forms on top of the surface. The zinc is so beneficial because it actually allows a sacrificial coating, leaving the metal to behave like a cathode, the underlying metal to behave like cathode, and it sacrifices itself, zinc sacrifices itself to actually protect the underlying iron or steel or other metals that it is covering on. So we can, as I said, we can do that by hot dip process. We can, by the way, we'll take up all these processes one by one in great details in the later part of the course. So this is just the preamble to many of these techniques. And the reason why we are talking about them is to put them together in the same place so that you know what are the very different variants that are possible. So in mechanically activated process, one can think of roll bonding or packed rolling. So where you if you happen to have seen certain sheets which are used as the cover for, say for example, your chocolate cover. I was about to mention to cigarette packets, but let me not do that. A much sweeter and better option is to refer to the chocolates sold by various companies. You have seen that the chocolate is wrapped very meticulously with a very shining foil, and that foil actually is a metallic foil, and at times that metallic foil also will have a thin polymer coating at the lower part. So the polymer coating has certain utility, but the metal coating essentially not only makes the chocolate appear more attractive, it also protects from ingress of moisture or any other atmospheric influence that can degrade the taste and the contour of the chocolate. So those are created by a special process where the aluminum foil, starting from a millimeter or less, is brought to a level of a micrometer or somewhere around that. So you can very well imagine that 3 orders of magnitude reduction in thickness dimension. And in fact, at that small thickness, the foil appears like a paper, so you can easily tear them apart. Otherwise, if you try and do that with a millimeter thick aluminum sheet, you'll never be able to do that unless you are a Superman. So, this roll bonding, pack rolling, diffusion bonding, these are all mostly bonding processes by way of mechanically activated, though it is diffusion bonding, but this is essentially through mechanically activated diffusion, so during pack rolling processes. I can create certain chemical layers on top, which is called CVD processes, chemical vapor deposition processes. So I take species into the vapor state and make them react in the vapor state in presence of a very active surface, which acts as a catalyst. So the species in the vapor state react and form a diamond-like coating, let's say. You create basically a carbon coating which will have a combination of sp3 and sp2 bonding, and then you get a very wear resistant and also several other good functional properties are imbibed. So that CVD, you can do an electro CVD, you can do a physical vapor deposition or PVD, or you can do, so these are all essentially thermally activated processes. Similarly, one can also use combination of thermal activation with velocity. Say for example, plasma spray or deposition essentially is a very special approach where you take the material in the plasma state, and I'm sure all of you would recall that plasma essentially is a quasi-steady state where you have neutrals, ions and electrons, 3 types. If you think of a neutral atom, by some means if you can take some of the electrons out, then it becomes an ion. So you have ions, you have electrons and also some neutrals. So these kind of a quasi-equilibrium condition is the state of plasma, which can be created by various mechanisms including thermal activation and reduction of pressure. So that plasma actually can do a very good surface modification either by removing material or even depositing certain species on top of an existing substrate. You can use thermal spray, which is, as the name suggests, is basically you activate materials to a very high thermally activated state and then you spray it on top, and because of plasticity, because of high temperature and diffusion associated with that, you create a thin or a thick layer depending on duration of the process. Another process, another extreme of that could be you could do either with thermal activation or even without thermal activation. The extreme could be the cold spray method, where you just take powders of certain geometry and size and throw at supersonic velocity on the surface of a substrate, and the substrate develops a thin coating, and eventually you can make a fairly thick coating by only spraying such powders at a great velocity so that the powders not only impact on the surface, but in the process of impact it also deforms and form diffusional bonding, grain bridges. So they stick to the surface and create a coating, and these coatings could be fairly thick. The novelty of such an approach is that you actually, in the limit, you actually can spray anything on anything. Whereas if you have to go by a chemical route or a thermal route or most of the other practices, then there are certain constraints or stipulations made by the thermodynamics of the process. In cold spray or high velocity spray, you actually can spray anything practically on anything. You can do sputtering, which basically is shooting specific atoms onto the. You first use something to remove atoms from a substrate. So you use a very high energy argon ion, which actually goes and hits the surface and scoops out some atoms from a target, and that target now, as a neutral, moves over a space, evacuated space, and gets deposited on a substrate which is kept somewhere around. In fact, while doing sputtering, you can also think of some reactive sputtering or reactive plating, where actually you create species of 2 different kinds or 3 different kinds, and during the flight, they actually are prone to reacting with each other and eventually deposit on the surface as a reaction layer. One can do ion plating deposition or plasma electrolytic oxidation, which is might sound to be sort of a very unusual approach. We spend so much time and energy to create the surface or to win metal value from its oxide or sulfide, the compounds, which is available on Earth as minerals and ores. And now you are saying that by using plasma, you would like to oxidize that surface. So this is actually a very clever approach, that it is almost like you would like to convert this into an oxide before nature or before atmospheric action makes it oxidizes it. So actually you are protecting the component by way of creating a thin oxidized layer by way of plasma electrolytic oxidation. Then these are fairly well-known practices of electrodeposition or plating, electroco-deposition, where you actually can have multiple deposition of multiple ions on the same surface. You can even go for electroless deposition or plating process, which is essentially a chemically activated process, and only a few species can be deposited on the surface without completing the electrolytic circuit of anode, cathode, electrolyte, and electrons flowing in the outer circuit. So that's why it's called electroless deposition process. So one very important point that we have to understand, I told you that the surface engineering is meant for modifying the surface microstructure and or composition for a very limited thickness. And generally we make a diplomatic statement, we say near surface region. Now what is that near surface region? Near surface region could be as thin as close to a nanometer. So I'm talking about 10 raised to minus 5 of a millimeter. So 0.1 nanometer or 100 micrometer. So that's kind of it can be, like 0.1 nanometer. And from that all the way to as thick as 100 millimeter. So actually when I say 100 millimeter, then I have built actually a component. And this is what mentioning here, that these days we hear a lot, and rightfully so, quite a bit of excitement about additive manufacturing. And additive manufacturing actually is nothing but building is a process of integrating droplets over a surface and then building such surfaces one upon the other. So when you develop a 100 millimeter or 10 centimeter thick layer, then obviously you would have built a new component, a new solid altogether, by adding layer after layer. So essentially we are talking about the limit of 0.1 nanometer to all the way to 100 millimeter. And in the process we see a plethora of surface engineering techniques possible. The thickest is one what we call weld overlay, which actually is very important for reclaiming or refurbishing worn components. We can use friction surfacing or friction stir welding, then thermal spraying, carburizing, carbonitriding. So look at the band, and that band actually tells you the thickness region that you can address. So for example, when you say nitriding, gas nitriding, then you're talking about typically a coating thickness which is limited to way less than a millimeter, maybe something like about 0.2 to 0.3 millimeter or 200, 300 micrometer. So then we go to shallower or smaller and smaller thickness, and then eventually come to ion implantation, various forms of ion processing, which are limited to only the few atomic layers on the surface. So that's why the dimension is 0.1 nanometer or so, or in the limit. So this is what is surface engineering, and surface engineering actually can allow various forms of coatings or surface modification of layers, and these are variable over such a wide thickness range. So surface engineering, we all are aware that we want to do it for designing the surface to be developed for various aesthetic purpose, for repairing and refurbishing. Right now I was saying that when you develop millimeters, even 10 centimeter, then actually you are building a layer so that this material can be used, or the component, maybe a roll, a part of a roll has chipped off. So would you like to throw it away, which is not only several tons, which costs several crores of rupees. So you would certainly like to reuse it. So there you use a weld overlay and then do grinding and make the surface conform to the exact curvature and dimension and thickness, and still continue to use it. So similarly, one can do joining and machining for conforming to specific dimensions or function. You actually may go for fabrication for finish dimension and use. You may develop and modify the substrate for a suitable, by using a suitable technique for a certain application. You may like to do characterizing and testing of the engineered or modified surfaces, and at the end, basically, you do surface engineering so that you can employ or deploy that component for various specific purpose, be it for cutting or be it for wear-resistant application, or just simply looking very good and pretty. So I think that's all. Thank you very much.